Okay, should we start?
Yes, sir.
Is my screen visible?
Yes,
So this is live session 5, and what we will discuss on? We will discuss on something called micro joining or nano joining, right? So what we will try to understand here, different kinds of micro joining and nano joining techniques like laser micro welding you have, then you have this electron beam micro welding, resistance micro welding, then basically, we will try to understand again the fundamentals of those fusion microwelding, and at the end of the session, we'll also have some numericals, right? So let's start then. So before going to questions, let us try to understand one by one different kinds of techniques over here. So, what is basically micro joining and nano joining techniques? So, if you see there, there is basically it's based on your characteristic dimension, right? Your sheet thickness, what you want to join, or the wear diameter, what you want to join. That should be smaller than a few hundred micron or something like that. And then, in terms of mechanism, what we can say, so in terms of mechanism of micro joining techniques, what do you have? You have one is this. You have to have this two ideally clean surface, right? Which need to be perfectly clean, and maybe if you want to check under microscope, it should be atomically flat, right? It also should be atomically flat, so that they can be drawn together spontaneously by some interatomic forces like that. And what is the driving force over here? What is the driving force? That is reduction of Gibbs free energy, right? That is the fundamental driving force for these kind of joinings. Uh, so you are basically replacing these high energy free surfaces by low energy interfaces. Now, uh, based on the physical states of the parts to be joined, we can differentiate those techniques into four different classifications, right? So if you have this four, so I'm using all the empty spaces over here, so don't be confused. Four different classifications. What are those for micro joining techniques? You have this fusion welding thing. Like in macro joining, you have these classifications over here also. The basic mechanisms are of course similar to those only. You have this solid state. What else? You have soldering or brazing. What next? You can also have adhesive bonding, right? Okay. Now, can anyone tell me what are different kinds of solid state bonding? Just a few examples. Anyone? What are different kinds of solid state bonding
Cold
techniques?
welding, friction welding.
Cold welding, friction welding. Exactly. Good. So in terms of solid state bonding, you have cold welding, you have explosive welding, you can have ultrasonic welding, can have friction welding. So friction in friction welding technique, there are different kinds of friction welding. So one is linear friction, then there is rotary friction. You are well aware of friction stir welding. I have already discussed that. Then in soldering or brazing, you have this what should I say? This active brazing, flip chip bonding, fluxless soldering. Those things are there. Those are different kinds of techniques which come under these categories, right? In fusion welding, you have this laser beam, you have plasma, you have resistance, you have gas tungsten. Those things are there, right? Now, if we try to understand these fundamentals of fusion microwelding, let us try to understand first this fusion microwelding. Okay, what is there in fusion microwelding? So this is also similarly controlled variable with variables like you have voltage, just like your fusion welding, gas tungsten or TIG, MIG, whatever you have studied, you know. So you have these similarly controlled variables such as voltage, current, and also travel speed also. Then you can have this continuous mode or pulse mode, right? So how will it look like in pulse mode? So it's like you can have this, let's say you have this power versus time graph. So you have this power versus time graph. So in pulse mode, you have this T on and T off time, right? So this time it will be on. Let's say this is some energy storing happening over here. Then again, this is on. So that's how it happens, right? This is my peak power. Are you guys following?
Yes, sir.
Yes, sir.
Sir, in continuous type mode, the voltage will be continuously constant.
So you will continuously flowing power. There will be no on and off kind of thing. You will basically flowing your current continuously over the time. There is no concept of T on and T off, right? So there will be no
Okay.
concept of number of pulses or frequency. So in pulse mode, uh, you basically aware of this how much your pulse frequency at 1 second, how many number of pulses you are producing over there. There is no concepts of like that in continuous mode. You are continuously flowing this current and voltage through your power source, right? Now,
Sir, what are the advantages of this continuous and pulse mode?
so in pulse mode, of course, you will always use this pulse mode thing you want to when you want to have this less heat affected zone. Hello, Am I audible now?
Yes, sir.
Hello?
Yes, sir.
Yeah. Sorry for the inconvenience. Yeah. Where I was? Pulse mode, right? So, yes, means if you are flowing your current and voltage continuously, you can have more amount of melting over a specific location, right? So, to reduce that, you can use this pulsed mode operation. Understood?
Yes, sir.
Hmm. Okay. So, next is in fusion microwelding, you have this in terms of basic phenomena. You can have this thermal aspects, you have this mechanical aspects, you also have this geometrical aspects. So there are different kinds of fusion microwelding, right? As I was saying, so you have this laser, you have this TIG welding, can have this plasma microwelding, then you have electron beam also, then you have resistance microwelding. Now we'll go through one by one. So let's say we are initially interested on this arc welding thing. Okay. So in arc welding, you have mainly this gas tungsten arc welding and also plasma welding, right? And here, big pulse, big power controls the penetration, right? And you can also have this regulated and control outputs over here also. And then in terms of this laser and plasma in microjoining, so in laser welding, you have this intense laser light which rapidly heats up the material in terms of some in order of some milliseconds. So it's basically kind of a non-contact process where you have this very little distortion of the final joint geometry and narrow heat affected zone. So these are some characteristic of the welding. So in macro thing also, those were there. So of course, compared to arc welding, you have this less heat affected zone, more precise welding, less distortion. Those things are there, right? So it's non-contact, less heat affected zone, less distortion also. Okay, and this is also precisely controlled. Yeah. And after that laser welding, you have this plasma welding, plasma micro arc. Where is there in microplasma welding? You have this low amperage capability. Then you have this arc transfer is stable over here. What else? You have short dwell time also possible over here. And the energy density is very high. Here also your heat affected zone will be less. So this is basically constricted over a narrow region. Constricted over a narrow region. Right? Now this is my fusion micro welding. Then you have this solid state micro welding. What is there in solid state bonding? Here also you have no melting of material. Then basically, as you have aware of that in solid state bonding, basically the joining is happening because of the plastic flow at the interface and those intimate contact are forming over there, right? So materials are plasticized over here. Materials get plasticized and form intimate contact due to material flow, right? Now, yeah, so what is there in friction welding? So we are discussing same thing again and again. What is there in friction welding? So here your heat generation is happening by friction, right? Either you are applying pressure or some extensive stirring of the materials. So you have this heat generation due to friction. You can join wide range of materials, including non-metals, and basically you can join dissimilar combinations also, right? And mostly in terms of this micro joining, this is preferably used to join components like heat sinks in electronic industry, right? So you can think of examples like aluminum heat sinks to aluminum substrate. Aluminum heat sinks to aluminum substrates. Now we have something called micro friction stir welding. What is there in micro friction stir welding? How you can differentiate from conventional to micro friction stir welding? In micro friction stir, you are basically downscaling your conventional friction stir welding with the sheet thickness what you want to join. That those are something like 1 mm or less than that. So in micro friction stir, sheet thickness less than equal to 1 mm, right? What are the applications? You will have this, as I was saying, this electronic connections, maybe some micromechanical assemblies, thin walled structures. Over there, you can use this micro friction stir welding. So, what is happening over here? It's like you are downscaling your tool dimension, right? You're downscaling your tool dimension. The tool which you are studying over your sheet surface. You cannot use larger dia tool, right? If you are using some large dia tool over a say 500 micron sheet thickness, what will happen because of axial thrust? It will basically tear up the material, right? That's why you have to have some, you have, just a minute. Yeah, you have to have some very small dia tool. So if you are having this small dia tool, because of friction compared to the larger dia tool, which one will generate more heat? Large dia tool will generate more heat due to friction, or small dia tool will generate more heat due to friction? Hmm. For which one Q will be higher? Q will be higher for
Sir,
large
it
diameter
depends
tool,
on
right?
thickness. Sir, a large diameter also. Sir, it depends on thickness also, sir.
So I am talking about cylinder.
Yeah.
So, thickness means let's say the height of the cylinder is same. So more contact area, more heat generations like that because of friction. So I can use some mathematical calculation also. Equal to tau into V. V is basically R omega. What is tau? This is contact shear stress. This is mu T. Mu T is mu Fn by As. R omega. It's like that. So Q will be higher for larger diameter tool. So in microfiction stir welding, what happens? You are using some very small dia tool, right? Because you cannot provide that much of thrust in a small thickness sheet over there because it can damage the material. That's why the process window over here is very narrow. The process window in the sense, what are the parameters you have? You have RPM, you have plunge depth, you have plunge rate. So you cannot play that much in between those parameters to get some successful joint. To get the successful joint, you have to optimize your process parameters in such a way that you can get some good successful uh, strain the in terms of mechanical strength, those kinds of joint. That's why I was saying this is process window over here is very narrow in a microfiction stir welding. What are the challenges over here? Here also you can see those exit holes. So, are you aware of this keyhole formation? Uh, Maybe you can check in Google. So, what what kind of tool you are using? You can use this with pin tool also. So there are two different kinds of tools, right? One is with pin and another is without pin. This is my shoulder. This is called shoulder, right? So when you are using some pin material over there, you are basically plunging this sheet metal, and this is my sheet over here. If this is my sheet material over here, and this is plunging and rotating, it will produce some kind of keyhole formation at your sheet material. Because when you are retract the tool from there, it will it will form those protrusion or tool impression over there. Because of tool impression, you have keyhole formation. So there are updated friction stir welding techniques where people are doing research to eliminate those keyhole formation. Like there you have this stationary shoulder. I will not go into detail of those things. Stationary shoulder friction stir welding. Then you have refill friction stir welding. So in refill friction stir welding, whatever keyhole formation you are doing, you are refilling with some additional material movement uh, from designing the tool in that way, right? Now, what else there in solid state bonding? You also have ultrasonic welding, right? What is there in ultrasonic welding? So in ultrasonic welding, you are displacing your interfacial oxides. Whatever oxide formation is there, whatever contaminants are there, you are displacing those contaminants using some pressure application or vibration application, right? So normally in ultrasonic welding. So here the removal of interfacial oxides or contaminants, that is there. Next you use this high frequency vibration with a low pressure to cause some kind of interlocking due to plastic flow at the interface, right? And if you see in ultrasonic welding, it can be characterized mostly by small rise in temperature. The temperature rise will be very less. So, what are the materials this is generally used for? This is mostly used for plastics, especially for joining some very thin sheet metals, maybe some 300 micron, 500 micron. It can be used for dissimilar materials also. And electronic industry mostly use this ultrasonic welding or resistance spot welding, right? What else there in solid state? We have talked about friction stir. You have talked about ultrasonic. There is diffusion bonding. What happens in a diffusion bonding? What is the principle of solid state diffusion? So it's basically the atomic diffusion happening over a period of time. So the atoms of two solids which are clean means you need to prepare the clean surface, right? And you are basically uh, putting those two metal surfaces. So if you have these two kinds of metals, you are putting those in vacuum furnace and you are heating it to isothermal temperature, let's say some T temperature from T ambient. So it's going to T ambient to T, and this is at vacuum furnace, and you can also apply a pressure to a plunger, right? So mostly depending on material combination, the heat what you are providing, that is in between zero point 0.5 to zero point 0.7 of melting temperature, some kind of recrystallization temperature along with this high pressure over time. That's how you experimentally do this diffusion bonding. And then what happens there that those asperities on those two surfaces, they come in contact with each other and they plastically deform, they interlink, and uh, that's how they basically diffuse into each other. So if you have, let's say you are joining some aluminum and copper are having two different atomic radius, two different atomic weight. So the diffusion rate of two different metals will be different. So aluminum will be diffused into copper at a different rate compared to copper, which will be diffusing into aluminum, right? So one metal will diffuse more into another metal. That's how it works when you are diffusing two different metal atoms into each other. And what are those advantages over here? There will be minimal distortion. There will be solid state, no melting thing. But the major disadvantage over here is it takes very high time, means longer time. Solid state bonding always takes very long time. So there are three, four mechanisms over there like grain boundary migration, then vacancy diffusion. I think you are well aware of this vacancy defect you are aware of, right? What is vacancy defect? Yes or no?
Yes, sir.
Okay. So those diffusion bonding technique is the fundamental principle is depends on this vacancy diffusion. So what happens like initially, let's say your metal surface was like this. So there will be, it's not flat, right? Atomically, if you see, there will be uh, the surface roughness over there. So let's say initially it was like this, and then if we try to zoom in, what will happen? From here to here to here, there will be material movement, and those asperities will plastically deform. Because of plastic deformation, there will be migration of these boundaries. Basically, the metal atoms are going into each other and they are filling up those spaces. And over the time, it will be like this. And at some point of time, it will coalesce over here. It will form a planar interface. You will see in a diffusion bonding, always you will find out there will be a planar interface, not a irregular interface, right? Now, how does this diffusion happen? I will rub it later. I have no spaces over here. I have spaces over here. How does this diffusion happen? What law does it follow? So, you have heard of this Fick's law of diffusion, right? There is something called Fick's law of diffusion. What does it tell you? You have this diffusion flux over here, and depending on your concentration gradient, so depending on your concentration gradient, that uh, location dependent concentration gradient, right? So at some location you have more concentration, at some location you have less concentration. So the diffusion will happen from more to less concentration like that. So here you have more concentration, here you have less concentration. Anyone here who is doing masters? So have you heard of this scanning electron microscopy? or have you seen any kind of uh, microstructure of diffusion interface? So we do something like something called line EDX analysis. If you have interest, you can Google it. So what do we do in line EDX analysis? Let's say you are diffusing two different materials, particularly for our case, let us assume we are diffusing aluminium into copper, or copper into aluminium. Okay. So when it will be diffusing into each other, it will form some diffusion interface. So this is my diffusion interface. This is my diffusion interface. At this diffusion interface, you will have both aluminum and copper at some specific composition and forming some specific phase depending on your temperature and pressure, which you can, uh, which you can, what should I say, which you can understand from phase diagram also. Now, why I am talking about this? Now, if you do some line EDX analysis, so you basically, let's say, scanning this cross section from aluminum to copper. So you will find out some, if we scan to find out what is the composition of different metals over there, what we see like this is aluminum, this is copper. So this is my total interface where there was 100% aluminum was there, and at the interface aluminum is starting to reduce, and here it is coming to 0%, and vice versa is for the copper. So here initially it was for 0%, and at the interface it is starting to increase, and then it is coming to 100%. So there will be this concentration gradient over there. This is my concentration, and this is distance. So depending on your distance, your concentration will vary during the diffusion process, right? And this is my sixth law of diffusion, J equal to minus d dc dx. And there is another term which you can equate with this diffusion flux, that is my time dependent diffusion flux. So what is there for time dependent diffusion flux? You have this J equal to m by n into T. What is m? M is my mass or amount of atoms being diffused. Is A is my cross sectional area, and T is time, right? And T is time. So at the end of the day, we'll get some equation to get this time of diffusion also. Is T is equal to, so this is basically you can equate this m by at, and that's how you can calculate this time of diffusion, and we'll get time of diffusion as, this is my expression of time of diffusion, right? So you can equate this minus d dc dx equal to m by at, and you can calculate this T from here. This I'm basically doing once again whatever you have gone through the video lectures. And how can you calculate those diffusion coefficients over there? How can you calculate diffusion coefficient? Diffusion coefficient is right here. QT is your activation energy, then R is your universal gas constant, then T is my temperature, then T naught. T naught is some temperature independent re-exponential term. So it's temperature independent. Re-exponential term that depends on materials being joined. Again, this will be empirical, depending on a material combination. That depends on materials being joined. Okay. Okay. We have talked about solid state welding also.
Here, D is equal to D0 exponential Q by RT or minus Q by RT.
Sir. Yeah, you are right. Okay.
Okay, sir.
Okay. What else do we have? Uh, what else do we have? We talked about fusion. We have soldering. Okay. We have talked about fusion. We have talked about solid state now. Then we'll come to this soldering or brazing. So I'll come to the question parts uh, finally at the end of the discussions, so that I will discuss everything all at a go, and then we'll just you can go through the answers. So what happens in soldering or brazing? Just a brief overview. What is difference between soldering and welding? So you basically use some kind of interlayer, right? So some kind of lower melting point material which can be drawn into the gap between those sheet materials that need to be joined. And because this is a lower melting point material, they basically melt at a very low temperature and fill the gap between those metals. And due to some capillary action and some flow of those metals, they fill those spaces, right? But there will be no melting of the components, the parent materials which you want to join. It's kind of filler material you are using. Enough. So yeah. So we talk about the soldering or brazing. Brazing is considered to be occurring at temperatures greater than 450 degree, and here those joints gain strain from the wetting of the parent metals. So you are using some low melting point material low melting point, interlayer material, different from those parent materials. Then basically wetting the surface, right? Wetting of the parent metals by molten solder or brass material, right? So any kind of contamination would cause some reduction in wetting and it will consequently lower the joint strength. And also, uh, always those gap between the parent materials influence the joint strength over there also. And if you see here, here also those both similar and dissimilar materials can be joined, and there are particular specific specific filler materials for specific parent materials which you want to join. Like for aluminiums, there are some soldered material called ALSI. I exactly forgot what exactly the composition is. You can Google it. I think this was an alloy of aluminium, silicon, and magnesium. So basically, what I want to say is there will be specific specific flux material or specific interlayer material depending on your material combination. Again, you cannot use any kind of material with any kind of material combination like that. And then you have finally is adhesive bonding. What is there in adhesive bonding? That's right. Hmm. What is there in adhesive bonding? So in adhesive bonding, it relies on what? It relies on attractive forces between the molecules at the surface of the adhesive and those of the surfaces to be joined, right? So in adhesive bonding, what does it depend upon? Attractive force between molecules at the surface of adhesives and those of the surfaces to be joined. Correct, no? Now, larger the molecules, better will be adhesion. So, larger the molecules, adhesion strength also will be better. That's why you can see those organic adhesives are commonly used. Now, the liquid adhesive is used to wet the surface which needs to be bonded, and this is then cured, hardened, and then they form some solid bond. So there are some concepts like curing and hardening to solidify those liquid adhesives. And this curing can be done at some temperatures, approximately at some again it depends on different adhesives. So mostly they range from 130 to 150 degrees C. Within those temperatures, and you have to provide some time to cure the material, right? And here, like brazing or soldering, the thickness of the adhesive should be minimal to provide a strong bond, right? The thickness should be less to provide a strong bond. Okay, sure. We'll come to the questions then. Let's try out this question. Which one should be the correct answer over here? We have talked about diffusion bonding, talked about soldering, solid state bonding, adhesive bonding, fusion welding. So these are the examples of different kinds of techniques. Which one should match with whom?
Sir, option 4.
Option 4. Let's see. Option 4. Diffusion bonding is, yes, diffusion bonding is solid state bonding. Then you have active resin, which is actually this should be resin minus 10. So this is a bracing technique. Yes, B is 1. Glassylene is the adhesive bonding. Adhesive sealing is the adhesive bonding. And glassylene is the fusion welding. Right? So this, this, this. Everyone agree? Everyone agreed, right? Okay. What about the next question? Let's adopt this. So you have this laser micro welding, then you have electron beam welding, plasma, and we talked about friction welding. Before that, before that, in laser micro welding, as I was saying that what is happening that at least one dimension of that part that should be less than 100 microns. Sorry, that should be less than 100 microns. At least one dimension of the part. That's how basically you can define it, but not always. And as I was saying, this is a non-contact technique with high intensity resulting from this. Basically, you are focusing a high intensity laser to a small diameter. So highly intense heat flux that is there. You can join both metallic and non-metallic. That's also there. You can use pulsed or continuous. There is something called laser transmission welding. That is a variation of laser welding. So, this laser transmission welding. What happens in laser transmission welding? So, in laser transmission welding, you are using some combination of a transparent material and an absorbing material that is used to fuse the transparent material. So this is a combination of transparent and absorbing material, where absorbing one is used to fuse the transparent material. That is called laser transmission welding. Now, in my past lecture, I have talked about this conduction mode. I have talked about this keyhole mode, right? So you have two different kinds of mode of laser welding. You have conduction mode, you have keyhole mode, correct? Now, in your conduction mode, power density is less, right? Your laser power is transmitted usually through some conduction to the surroundings. That's why it is called conduction mode. And here also the penetration will be controlled by the conduction mode. But what happens in keyhole mode? Here the power density is very large. That exceeds something around 10 to the 6 watt per centimeter square. That exceeds. So here power density is higher than 10 to the power 6 watt per centimeter square. Let me drop this up over here. So, huh. And in keyhole mode, what happens is molten metal starts to vaporize. Just a minute, guys. Huh. So, what I was saying, molten metal starts to vaporize over here in keyhole mode operation, and it basically opens up some blind hole, opens up some blind hole or keyhole in the molten metal, opens up some hole, and here the the mechanism is like this, the vapor pressure from the hot metal that keeps the hole open during the weld. So if you form this kind of keyhole over there, we call it something called recoil pressure, or the vapor pressure over there that keeps the hot metals open during the weld. Yeah, and there are these different pulse shaping in laser micro welding also. So in pulse shaping, what I mean to pulse shaping. So you can use some kind of profile like this, upslope at the beginning and then downslope at end. So why you want to use upslope at the beginning? This prevents some thermal shock. This downslope can control the cooling. Then also you can use high peak power initially to start melting. Then whenever you have this melting, uh, whenever you have this molten material, the absorption rate increases, right? And then you reduce the power. That's why you basically shape up your power distribution over time, depending on a different material combination. Now, if you are heating up some crack sensitive materials, if you are heating up some crack sensitive materials, you have to use some low peak power initially to melt the first material, and then you can again increase the. If you do some sudden increase of the power in the power distribution, it will initially crack it up, and then the complete process will get damaged, right? Okay, so coming to this, what should be the correct one? We have laser beam welding, electron beam welding, microplasma, and friction.
Sir, is pulse shaping used to control the peak power?
Mm-hmm.
Sir, is pulse shaping used to control the peak power also?
Not getting you.
For controlling the peak power, is there any role of this pulse shaping?
Controlling the power.
Peak power.
Yes. The pulse shaping you are talking about.
Yes, sir.
Yes, controlling the peak power. Right. So you're basically varying the peak power over some pulse on time,
Yes, sir.
right?
Okay, sir.
So what will be the correct one over here?
The answer is also 4 here. Option 4 here, sir.
Option 4.
Sir, I think option 3 is correct.
Let us check. So we have this laser beam welding, heat generation by friction. This is this friction welding.
Friction welding.
Okay, so there is no need to check A3. In laser beam welding, you don't use vacuum condition. Yes,
Sir,
option
in
3 is correct.
electron beam welding, we use vacuum.
Yeah, do you agreed? The others. So in electron beam welding, you use vacuum. In laser, you don't use vacuum, of course. This is well aware. In friction, you are heating up the material through friction. And as I said, for microplasma, you always form this stable arc at low current. So option 3 is correct over here. What about question 3? It says materials that are susceptible to deformation or cracking can be joined by ultrasonic bonding. It's fine. Uh, in the reason part, it says actually both are true, but is reason is the correct explanation of this? Materials that are susceptible to deformation or cracking. This is not a correct explanation. Okay, let's move to the next question. What does it tell about? Which of the following statements are correct about microplasma quelling? A stable and concentrated arc can be achieved at a lower current. This is true. One is true. One is true. Then two says shorter world times are possible. Two is also true. The three says of course not. Width of the hypervector zone is dash. This is false. And four is with lesser frequency occurrence. Four is true. So D is correct. Agreed?
Yes, sir.
Okay. Moving to next one. Which of the following statements are correct about soldering or brazing? So it says brazing is considered to occur at a temperature. This is true. One is true. Soldering is generally used for joining wire in printed circuit boards. That's also fine. This is not true. Three is false. That's fine. Four is true. C is correct. Agreed? All agreed, right? I'm moving first because we have numericals at the end. Should I move to next question or do you have any question? Okay. What about this one? Which of the following process parameters of ultra-short pulse laser welding is used to determine the time in which energy is stored in electrons? Okay, can you first tell me what are different process parameters over here? So you have pulse energy, you have pulse energy. What does it tell you? this energy delivered in a single pulse, right? I'm not writing everything. Then you have power density. What power density dictates? This is number of laser photons which impinging on the material. So density of the power, the number of laser photons, those are impinging on the material. Then you have pulse duration. What is pulse duration? The length of the time that the laser energy pulse is on, right? That is my pulse duration. Then you have peak power also. What is there in peak power? Maximum power over a pulse on time. Then you have pulse frequency, number of pulses over a period of time, right? This pulse frequency. What else? We have photodiode also, and have laser focus photodiode, and we can have some relaxation time. So within these parameters, which one will use to determine the time in which energy is stored in electrons?
Sir, I think relaxation time.
Yeah. So during a relaxation time, what happens? This is the time in which energy is stored in electron. After this time, it will be converted into the heat. So here the energy is getting stored, and then it will be releasing as heat after the relaxation time is over. Okay. Okay. About this one. So how will be the characteristic basically of the pulsed current in plasma? Then you can uh, then we can come to this question: characteristic of pulsed current in plasma arc. So what are there? Okay, before that, do you remember those? Do you remember? Do you remember the concept of? Yeah, leave it. I thought if you can remember those electron beam moving, anyhow you can go through the video once again. Leave it. So coming to this characteristic of pulsed current in plasma, how we can characterize a shaped current. So let's say this is my time and this is current, and I'm having a profile like this. Okay. So what is this? This is the current, or if you are thinking of power, This is my peak power, right? And what is this? This is my base power or base current. So if you're thinking of current, this is base current. If you are thinking of, so power is equal to voltage into ampere, of course, right? Now, what is pulse width? So pulse width is the duration of the laser pulse. So this is my pulse width, the duration of the laser pulse, right? And then what is the pulse energy? The energy contained within a pulse is a product of the power and the pulse width, correct? So energy is basically power into P है ना? And then you have this average power, and then there is something called pulse repetition rate. So it's basically is expressed in terms of hertz. So pulse repetition rate is the number of flash lamp pulses per second. So my pulse repetition rate is the number of pulses per second. Let's keep it simple. Number of pulses per second. Okay. Now tell me, which one should we look at it answer?
Sir, option, I think option A, sir.
Option?
Option A.
Option A. Okay. Let me check. So the pulse repetition rate, this is number of years, A4, and B pulse setting, this is used for enhancing years, B2, and C2, duration for this pulse years, and you have, okay, yeah, so option A is correct over here. Uh, I think I've left one resistance micro welding, right? Huh, I left it that. Anyhow, the basic mechanism is similar in just like resistance welding. So depending on your resistance of substrates to the passage of the electric current. That's how it works. And Joule's heating is there. So the heat, whatever is getting generated, that depends on the current, whatever is flowing through the material, your electrical resistance of the material, and the time, right? So, here is equal to as per RT. So that is the fundamental principle of resistance welding, and that remains same for micro welding also. Now, what is the difference from the macro scale? So here the electrode pressure is much lower in micro welding, of course, and your much lower electrode pressure that results in higher contact resistance. So your electrode pressure is less, contact resistance will be higher. This you are agreed, right? So that reduces the welding current. What you want to flow through the material, and for this there will be some sticking kind of behavior. So that promotes sticking of material with the electrode. correct? Now, this kind of micro welding mostly used for non-ferrous metals and alloys such as copper, nickel, platinum, aluminium. For regular welding, you can use mostly steels also. Okay. Can you give me a quick answer? So you have titanium, silicon, lead-free solders, polyurethane. Now, if you're talking about this, so I think over here, A should be resistance welding. For silicons, normally we use adhesives. For the solders, which are lead free, you can use ultrasonic. For the other one, you can use laser. Okay, we'll directly go to the numerical part. Sure. So you have this pulse laser micro welding process where the scanning speed, the pulse energy, the pulse on time, the pulse frequency, those data are available with us. So we want to find out what is the peak power, what is average power. Uh, Fine, if you are having this peak power, average power is um, divided by 2. What is heat input per unit length? What is pulse off time? So what is peak power? Peak power is pulse energy, right? Pulse on time, right? So how much is my pulse energy? 6 joule. How much is my pulse on time? Is 5 milliseconds. 1.2 into 10 to the power 3 watt. All agreed? So if this is my peak power, average power is be 0.6 into 10 watt. Then what is the heat input per unit length? So heat input per unit length. What is that? It is Q by V. Q is the field flux divided by the weld speed. So I have my peak power. Peak power is 1.2 into 10 to the power 3. That is in watt, joule per second. And this is in 4 mm per second. How much is this coming? If anyone having any confusion, tell me. What is my calculator? Okay, can you please calculate? I am not getting my calculator. 1.2 by 4 and 3 into 10 cube joule per mm. Correct, no?
Yes, sir.
Hmm. So I got the heat input per unit length also. Then I need to find out what is pulse of time. How can we find out pulse of time? So we have the pulse frequency over here. So my pulse frequency says number of pulses per second. So 20 pulse per second, right? So how much will be the t on plus t off time? How much will be the t on plus t off? If there is 20 pulses per second, so one pulse will be taking this much of second. है ना? So t on plus t off is equal to 0.05. Now what is t on? 0.005. Correct? So t off is coming as 0.045 second. All good? Anywhere is there any confusion? Or we will move to the next question. Okay, let's move to the next question. So it says in a diffusion bonding process, the mass concentration of carbon in parent material is 0.2% over the time t and a fixed pressure. You were increasing your carbon percentage to 1%, which is measured at 0.2 mm depth of the sample, and you can assume the process is carried out at 800 degrees C. The activation energy is provided, D naught is provided. We have to estimate the time requirement T to reach such diffusion of carbon, the volume normal to the depth direction. So we know the equation of this time of diffusion, right? So you know equation of time of diffusion. This was my equation of time of diffusion. Now what is D? D is D naught exponential of minus Q by RT, right? So my D naught is 0.7 into 10 to the power minus 4. That into e to the power minus q by RT. What is q? Minus 157 into 10 cube. That divided by, I know the universal gas constant. That into 800 degrees C is how much Kelvin? 1073.
1073.
Yes. How much is this coming? This will be coming in terms of meters square per second. So these all are in SI units. How much is this coming? Anybody?
Sir, it's coming 3078.08.
708.08. Sure.
3078. Sir, it comes 3078.08.
Is it okay? Sridhar, you want to speak?
Sir, I got a different number. It is 1.6 into 10 to the power minus 12.
10 to the power minus 12.
I
This is
think I
completely
did some
different.
wrong in calculation.
How much you are getting?
1.6 into 10 to the power minus 12.
So, which one should I consider? Okay, whatever. Let us assume we have got the d value. Just get the concept anyhow. So, that's how you can find out the d value, right? Then I can find out how much is my concentration gradient, correct? How can you find out concentration gradient? So these things are provided over here. You have this carbon percentage in kg per meter cube. So you have this 0.2 minus 1 rho, so then kg per meter cube, and that divided by is in 0.2 depth. So 0.2 into 10 to the minus 3, that is in meter. Okay. So 0.2 minus 1 is 0.8, 0.8 by 0.2,
Sir,
4.
it comes 1.6 into 10 to the power minus 12. It is
Okay.
right.
Okay. So we have two people, we have got this 1.6 into 10 to the minus 12. Fine. So here I am getting minus 4 into 10 to the power 3 into rho kg per 10 to the power 4. This I can calculate with a small calculation. Okay. So I have find out dc dx in terms of rho. What else do I need? We need m by a value, correct? Now m is my mass, right? Mass is A into G into rho. So rho into volume, correct?
Sir, here D is depth.
Yes, this is depth of diffusion. This is right, right? So then if you have this mass area into depth into rho, so m by a is depth of diffusion into rho. You know the depth of diffusion is 0.2 mm. So finally, what you are getting? This was my D value. This is my dCdx value. And this is K into rho. So minus 1 by 1.6 into 10 to the power minus 12. That into what is depth? 0.2 into 10 to the power minus 3 into rho into this is the dCdx value, right? That inverse. So 1 by minus 4 into 10 cube into rho, right? So I'm not getting into the answer. This will take time. So up to this, you are agreed or not?
Okay, sir.
Okay.
Yes, sir.
Okay. So let's move to the last one. It says in a resistance microwelding process, you have the applied voltage that is 2 volt. We have the overall contact resistance 2 into 10 to the minus 4 ohm centimeter square. What is the amount of it? So as I was saying, Q equal to I square RT, right? Now we don't have the ampere. How can you find out the ampere? So this is V equal to I into R. So let's make it capital. So I is equal to V by R. So V square by R square into R into T. V square into T by R. Now it asks me what is the amount of heat generated per unit area. Heat per unit area during the process. Also, time is not provided here. ठीक है, heat per unit area, we can take per unit time. Right? So if I am asking you per unit time heat, so that's simply V square by R. V square is 2 square, 2 into 10 to the minus 4. 2 into 10 to the 4 per centimeter square. I should have provided the time. It's fine. Okay. Anybody, any question? Okay, then let's stop it here.
Okay, sir. Thank you very much.
Thank you. Bye.
Bye.
Thank you, sir.